A very good afternoon to all of you, and uh, I'll be talking about space quantization. As we have already talked about in the previous lecture, I talked about the magnetic moment of an electron in a one electron system. We obtained an equation for the measurement of the magnetic moment of an electron, of one electron atom. And now we will be extending the idea of space quantization. And as we understand that if we have an atom and we subject this atom to an external magnetic field, say I have an atom, I apply an external magnetic field on it, there are only certain orientations which are permissible for the angular momentum of the electron in this atom. Now having these discrete values of angular momentum for an atom, when you subject this an atom to an external magnetic field, leads to what is called as space quantization. And as we know, we already have switched our understanding of quantization of orbital angular momentum by solving the Schrodinger's wave equation on hydrogen atom. And here, what we are trying to describe is that when you are subjecting this atom to an external magnetic field, so you have an atom, you subject this atom to an external magnetic field. So in that case, what we have, we'd like to go with that mathematical treatment and understand this space quantization in numerical sense. So if I assume that I have an angular momentum vector L, and this angular momentum vector L is due to the motion of an electron. Say an electron is moving in the orbit, and when we switch on magnetic field, say we switch on magnetic field in the Z direction. So when we switch on the magnetic field in Z direction, there is the precession. There's precession of the angular momentum, and the orbit of the electron precesses. This orbit of the electron precesses towards the magnetic field. So this is my magnetic field which I am subjecting, assuming this magnetic field to be in the direction Z, and there is an angle between the orbital angular momentum and the magnetic moment, assuming this angle to be equal to theta, right? And if I draw a perpendicular from here on the magnetic line, so if this is perpendicular and this is L, it will have a component along the magnetic field, and let's assume that the component of this angular momentum along the applied magnetic field is Lz. So this is Lz, and we can see here that we have a right angle triangle, and we can write down cosine theta. So cosine theta will be base. So the base is Lz. It will be Lz divided by hypotenuse, and hypotenuse is L. Now, maybe this is the basic equation that can give us an idea about the space quantization when you subject your atom to an external magnetic field. Now, we can see here that this L for one electron atom, we have already calculated this L by solving the Schrodinger's wave equation, and this L, the magnitude of this L is under root of L times L times L plus 1 H bar. So this is the magnitude of the orbital angular momentum, and the magnitude of the angular momentum along the Z component. And what's that? The magnitude of this angular momentum along Z is nothing but mLh bar. And we understand that this ml can take the values from minus L to plus L. So we have L and we have LZ. LZ is mLh bar. So if I use for LZ and L in this equation, I will have cosine theta. I will have cosine theta equals ml h bar by under root of L times L plus 1 h bar. And this h bar and h bar can be cancelled, and we will have ml divided by under root of L times L plus 1. Now, the question arises here, we have ml. So if I write down this equation as cosine of theta is ml by under root of L times L plus 1. Now, what we understand from ml point of view, I mean, we will have ml as ranging from minus L to plus L. We will have this much of values for particular L. So for particular L, I will have 2L plus 1 values of ml. And if we choose an example here to understand this equation in numerical sense, for that, if I choose, say, for example, I choose L equals, so what I have cosine of theta equals ml by under root of L times L plus 1. Now, if I choose that this L is equal to, say, for example, I'll take this L equal to 2. So ml will be how much? ml, it will be, say, it will be minus 2, it will be minus 1, it will be 0, it will be 1 and 2. So these will be the discrete values of ml. And these discrete values of ml is a result of the magnetic field that we are applying in the z direction. So what will be Lz? So Lz will be minus 2h bar, then it will be minus h bar, 0, h bar, and 2h bar. So there will be 5 quantized orientations of the angular momentum. So the values of angular momentum can be seen here. For this purpose, we will have 5 values of angular momentum in z direction. Now, what we want to understand in addition to this is we have L quantized, we have ml quantized, we have cosine of theta. This means that cosine of theta will also be quantized. And if cosine of theta is quantized, then theta is also quantized. So for this particular example, we have 5 values of ml. That means we will have 5 values for cosine of theta, and automatically we will have 5 thetas. So we will have discrete thetas. We will not have all possible, we will not have all plausible values of theta. We will have only a set of values of theta, confirming the quantization, confirming the existence of the space quantization in this atom when it is subjected to an external magnetic field. Now, one more thing, if we see, if we calculate this under root of L times L plus 1, for this particular case that we have chosen, it will be under root of 2 times 2 plus 1. So L is going to be under root of, this is 3 times 2, this is 6 H bar. So the value of this is equal to under root of 6. And under root of 6 is, of course, it is greater than 2. And if we look onto the numerator of the given problem, of the given example, the numerator is never greater than 2. The numerator is either less than 2 or it is equal to 2. So ML is less or equal to 2. So we have the numerator, and this numerator is less than 2 or equal to 2 at the most, and we have the denominator. Denominator is greater than 2. So you have smaller than 2 numerator, you have greater than 2 denominator, leading us to the fact that the value of this cosine theta will not be equal to 1. It will not be equal to minus 1. So when cos theta is equal to 1, theta equals 0 will give us 1, and theta equals 180 degree is going to give us minus 1. So this means that you cannot have quantization when the direction of the magnetic field, suppose this is the magnetic field, and the angular momentum is in the same direction. If the applied magnetic field and the angular momentum, if they are in the same direction, in that case, you will not obtain the value of quantization. You will not have a value. So similarly, if your magnetic field is in this direction and your angular momentum is opposite to the direction of the magnetic field, you will again not be in a position to obtain the quantization. So this way, we have some exceptions here. So we can have only some set of values. So we'll have theta 1, we'll have theta 2, we'll have theta 3, we'll have theta 4, and we'll have theta 5. We'll have 5 sets of angles that can be projected by applying a magnetic field to the electron in the z direction. And we can draw this thing, and what we have is, we have a situation like this. So this is my 0, this is 2h bar, this is h bar, and this has to be 2h bar. This is minus h bar, and this is minus 2h bar, right? So corresponding to this, so this is over LZ, and this is the direction of the magnetic field, and this will be 2h, this will be h, and this will lead to 0, and this will lead to minus h bar, and this will lead to minus 2h bar, and we can project it in a semicircular way. So here what we have is the space quantization of the atom. Space quantization of the one electron atom. So you apply a magnetic field in z direction, and you have a projected angular momentum vector of the electron revolving around the nucleus, leading to only the discrete values of the angles that can be projected, the discrete values, the discrete directions of angular momentum, when you are subjecting this atom to an external magnetic field, this is what is called as space quantization. So with this, I would like to say goodbye and have a nice time.